So welcome to this TeachElectronics.com presentation of binary to decimal conversion. What we're going to do is we're going to teach you how to convert. And there's only one learning objective. At the end of this lesson, you're going to be able to convert binary numbers to their decimal equivalents. So take a look at the examples at the bottom. Notice that there are 5 decimal numbers, 1, 7, 10, 64, and 100. And over to the right are their binary equivalent. So the number on the right, 7 zeros and a 1, that's the same equivalent, that's the same number as 1 in decimal. If I were to write the second number down in binary as 111, those 3 ones represent the number in binary that is decimal 7. So what we're going to do is we'll pick a couple of random binary numbers and we'll walk through how it works. Now you probably noticed in the binary column that there's a lot of leading zeros. And you also know that in the decimal system, we don't really use leading zeros. Writing 00046 is not the way we write the number 46. Over on the right are the same numbers as the binary numbers in the center column, but they have no leading zeros. And we're going to see a lot of leading zeros. So let's talk about how that works. In computers, most binary numbers, and we don't store decimal numbers, there's no place to store a 7 or a 6 or a 4 in a computer because the only thing you can store in a computer are the numbers 1 and 0. So you have to figure out kind of a secret code that changes the numbers we know of as 6 and 4 and 3,000 into only 1s and 0s. And of course, that's the binary code that you see here. In computers, binary numbers are always stored in multiples of 8 bits or 8 digits. I'm going to interchange the word bit and digit. They both mean the same thing. It's one of the digits of a binary number. Any number in a computer is stored as a sequence of 1s and 0s, but they're always stored in multiples of 8. We either store 8 bits or 8 1s and 0s or 16 bits or 32 bits. We usually store a number of bits divisible by 8. When we store the number 1 or 7 or 10 in binary, which is the third column over on the right, when we think about it, we don't think about those leading zeros. But when we store it, we're going to store them in a storage place that requires 8 1s or 0s because each of those 8 memory storage places has to be either a 1 or a 0. So we use those leading zeros to say there's no 1 here, there's no 1 here, there's no 1 here. But they still have to be there because you can't have nothing in a computer. I can't store 7 nothings and a 1. I can only store 8 1s or 0s or any combination of 8 1s or 0s. What we do is we put the leading zeros in whenever we store any number that has less than 8 bits. And the same thing with 16 bits. If we have 16-bit numbers and our numbers less than that, we zero fill or left fill with zeros any binary numbers to get to that even number of 8 or 16. Although the numbers on the right are the real binary numbers, you'll often see them with the leading zeros, meaning that this is how we're going to store it in a computer. So get used to seeing both or either. They're both correct. I'm going to use the leading zeros in this presentation because we're going to act like our binary numbers are going to be stored in a computer. So I want you to get used to seeing them. Well, we're going to talk about column weights in this presentation, so we need to understand what that means. What I've done, I put the decimal number 101 and the binary number 101 up on the screen. So I want to talk about that a little bit. You all know, if I tell you what is the number 101, how much is that? That's real easy. You're going to say 101. You're going to say that because you understand the decimal system. You've been trained since you were a tiny child how the decimal system works, and you've been trained with column weights. You've been trained that the column weight of the 1 on the right is 1. It represents one thing or one unit or $1 or one of whatever we're counting. The 0 in the center, you've been trained to realize that that 0 is really the tens column. And this tells you how many tens are in the number. In this particular number, there are no tens. And of course, in the third column, you're taught that this column, a number in this column, represents the number of 100s in your number. So in this case, you can look at that number and say there's 100, there's no tens, there's 1. So we have the number 101. Binary counting over on the right isn't anything like that. We don't use column weights of 10. We use column weights of 2. So our column weight columns go 1, 2, 4, 8, 16, 32 instead of 1, 10, 100, 1,000, 10,000, and so on. So you need to get used to that column weight system and realize that number 101 is a different quantity than the decimal 101. And another thing we do quite often is we provide subscripts. I'm going to put the subscripts up here. You can see the subscript in decimal 10 and the subscript in the binary number of 2. Here's what that means. The subscript 10 says, I am a base 10 number. I am a decimal number, and the decimal numbering system has a base of 10 because each of the columns is a multiplier of 10. So it's a base 10, and we have 10 numbers that we use to count. On the right-hand side, you'll see the subscript 2 on the 101. And what that tells you is this is a base 2 number. Everything in this system is based on powers of 2 instead of powers of 10. The first column on the right represents a 1. The next column to the left represents a 2, then a 4, then an 8, then a 16, and so on. We'll talk more about that in a minute. For right now, just so that we're not confused, when I show you the number 101, I'm going to put the 10 up there or the 2 up there to remind you that the 101 base 10 or the 101 subscript 10 is a decimal number. And on the right, the 101 base 2 or the 101 subscript 2 represents a binary number. How do we determine what a number is? The decimal is easy. Again, you've been trained in that and taught on that ever since you were born. Now, you probably weren't taught exactly this way, but I'm going to lay this out for you in a powers of 10 format. What's in the green box on the left represents the third digit. What's the third digit represent? And we can see here it says 1 times 10 squared, or 1 times 10 to the second power. Well, 10 squared is 100, so 1 times 100 is 100. So in decimal, a 1 in the third position from the right represents the quantity 100. If it were a 2 inside the green box here, we would write 2 times 10 squared, which would make it worth 200. That's the column weight. The column weight of this column is in the hundreds. Well, looking at the center column, in this case, there's no tens, and that's 10 to the 1. This says 0 times 10 to the 1, meaning it's 0 because that's what's in that digit, the 0. And we multiply it times 10 because it's the 10 column. And 10 to the 1, or 10 to the first power, is 10. So this says 0 times 10 is 0, so we don't really add anything. So far we've come up with 100 from the first digit, nothing from the second digit. And the third digit, the 1, or the first digit on the right, represents 1 times 10 to the 0, and 10 to the 0 is 1, so 1 times 1 is 1. So the third digit is a 1. This tells us that we have 100 plus 0 plus 1, or 101. That's how we figure out what the number is, or how we figure out how large the number is, or what its quantity or size is. Well, in the binary numbering system, it's exactly the same. The only difference is, notice that the exponents are still the same, 2 and 1 and 0. Notice that the 1 times or 0 times are still the same, but notice the number now becomes 2. 2 to the second power, 2 to the first power, 2 to the 0 power. Why? Because it's a base 2 system. Later, when we learn octal, which is in base 8 system, those 2's are all going to get replaced with 8. And later, we'll get into the hexadecimal system, which is a base 16 system, and we'll replace all of those 2's with the number 16. So they're all the same. It's just that each column has a different weight based on the power of the base. This 1 in the third column says we're base 2, that's the 2, and 2 squared is 2 times 2 is 4, meaning that the third column has a weight of 4. So 1 times 4 is 4. So the 1 in this column represents the quantity 4. Well, we move over here. Same idea with 0. There's nothing in a 0 is worth nothing. And this happens to be the 2 to the 1's column, or the 2's column. This says there's no 2's because 0 times anything is 0. So there are no 2's in this number. And then lastly, the far right-hand digit is a 1, but it's 2 to the 0. And anything to the 0 is a 1. So 1 times 1 is 1. So what this number says is add 1 times 2 squared, which is 4, plus nothing, which is nothing. We still got 4. And this last equation over here, 1 times 2 to the 0, represents the number 1. So this means 4 plus 1. So when we do that, we lay it out. I'll lay them both out here for you. We'll say that the decimal number 101 represents 100 plus 0 plus 1, or what we know of as 101. The 101 in binary means something totally different because we use different column weights. And this number says 4 plus 0 plus 1, or 5. In the decimal system, the number 101 represents 101. In the binary system, and I made a mistake there, it's a 10. That should be a 2. Should be 4 with a 2 subscript. Made a mistake. So the 4 subscript 2 represents that this number is 4 in the base 2 system. So that's how the base systems work. Let's figure out how we change the numbers. We start out with a blank piece of paper. Start out by writing the number 1 at the top right. As I've done here, on here I've made it brighter. I've dimmed the numbers that are coming up. After you write 1, go to the left of it, write a 2. And then you're going to keep doubling the number all the way as far to the left as you want to go. Oh, so we double a 2, we get a 4, double 4, we get 8, double 8, we get 16, double 16, we get 32, and we continue doing that. Now, how long do we do it? Well, since we're working with 8-bit numbers, we've got to have 8 numbers up top. We have to have 1 to represent every bit in the 8-bit number. So as you can see, the 1, 2, 4, 8, 16, 32 represents 6 numbers, but we're going to use 8 bits, not 6 bits, so we're going to write 2 more numbers. So we'll double the 32 to 64, double it to 128. Now, these numbers will stay at the top of the page, and we'll write our binary number under it, and then figure out what its value is. Pick a number. I just picked a couple of random numbers. Down at the bottom of the page, you'll see 10, 10, 10, 10. I just picked that because it's a nice pattern. Okay, and I picked the one to the right because it's just a number. It's ones and zeros. So what we're going to do is we're going to take each of these 2 numbers. We're going to walk through the conversion process so that you can easily figure out what the number 10101010 base 2 represents in the decimal numbering system. So here we go. Well, let's work on the first number, the 10101010. That's the number. We're trying to solve the problem, what is that number worth in the decimal numbering system? Remembering that each of the digits in a binary number has a specific column weight. What that 1, 2, 4, 8, 16, 32 up top says is the farthest bit on the right in an 8-bit binary number has a column weight of 1. The next number, the 2, means the next number over, the second from left in a binary number, has a column weight of 2. The next bit, a 4, the next bit, 8, and so on. So we're going to walk through 1 bit at a time, and we're going to add up those numbers to see what our total is. We're going to add up the column weights, and you're going to notice these zeros. We've got some zeros in our binary number. We're not going to add anything if we hit a 0. So let's start with the right-hand bit. The right-hand bit is a 1. And down at the bottom in our binary number, it says, well, the binary number that we're solving for has a 0 in that bit, so there are no ones in that number. So we don't add anything to our total. We start our total at 0, of course, and we say, well, how much do we have to add up to get to the number we're looking for? This 0 in bit position 1 tells us, well, there's nothing here. There's no ones. So let's move to the next bit. Well, the next bit is a 1, and if we look up top, we see that that's column weight of 2, meaning there is a 2 in this number, so we need the quantity 2 to be in our number. So we're going to start adding numbers up, and the first number we're going to add is 2. We'll put a box over on the right, and we'll say, okay, because there's a 1 in the second bit, and the weight of the second bit is 2, we know our number, our total, has a 2 in it. So we'll place a 2 in the box, and we'll keep looking for numbers in this box until we've added up whatever we need to get the correct total. Now, as we move left from this second bit, you'll see we have 3 zeros in different positions in the 8-bit number. We can ignore those because if the zero's under a 16, it means there's no 16s in the number. You don't have to worry about it. If the zero's under a 32, then you say, well, we don't have to worry about that. So we can ignore the 2s and just look for the value of the 1s. So here's 1. Now, this 1 is located in position 4, if I'm counting from the right, 1, 2, 3, 4. It's the 4th number over from the right. It's a 1. Well, what's the 4th number at the top of the page? It's an 8. This column, or this 1, represents the column weight of 8. So that means there's an 8 in our number that we have to add. So we're going to add that 8 to our total. So far, we've got a total of 10. We're going to keep going as long as we have 1s, and we'll eventually get the correct total that'll give us the sum of all these numbers, therefore, what its decimal value is. Well, the next 1 over is in the 6th position from the right, and if there's a 1 in the 6th position from the right, it means that that's the 32 column weight column. So we're going to need to add 32 to our number to find out what the total is. Let's move the 32 into our sum. We've now summed 3 numbers, the 2, the 8, and the 32. We only have one more 1, so we can move to that one. And we can say the last 1 in the number, the far left bit, the 8th bit of a binary number has a column weight of 128. Therefore, we need to add 128 to our number. So when we add 128, we wind up with a grand total of 170. And 170 is the correct answer for what is the decimal value of this binary number. So down the bottom, we can replace our answer of 3 question marks with 170 subscript 10, meaning in the decimal system, that's the subscript 10, this number has a value of 170. So we're done filling out this number. Now, I did it kind of the long way. When we do the next number, I'll show you a shorter way. And it's quicker once you get used to it. But I wanted to get you to understand that each column weight goes up 1, 2, 4, 8, 16, 32. If I was teaching the decimal system right now, guess what I'd do? I'd write 1, 10, 100, 1,000, 10,000, 100,000, okay? I'd keep adding a 0 to each of the number or multiplying by 10 each time. That's what the decimal number means, base 10. Each column goes up times 10. This is a base 2 system. Each column goes up times 2. So as long as we write these numbers down, 1, 2, 4, 8, 16, 32, 64, and we put a 1 or a 0 under each of those numbers, we can figure out what the total of the number is. Let's take a look at the right-hand number on the bottom, 0011, 0110, subscript 2, meaning it's a binary number. So we have this 8-bit binary number. It's got 4 1s in it. What columns do those 4 1s represent? Well, the 2 1s on the right represent the 2's column and the 4's column. Remember now, if this was decimal, that would be the 10's column and the 100's column. You need to be able to shift back and forth between the powers that we're talking about. Right now, we're talking powers of 2. So we know we have a 1 in the 2's column, 1 in the 4's column, 1 in the 16's column, and 1 in the 32's column. So, of course, what that means is to find out what this number is, add the numbers 32, 16, 4, and 2, and we'll have our total. And so, sure enough, if we add up 32, 16, 4, and 2, we're going to get the number 54. 2 plus 4 is 6, plus 6 is 12, plus 2 is 14, carry the 1, 3 plus 1 plus 1 is 5. So the number is 54. We can now, at the bottom right of the screen, replace those 3 question marks with the number 54, meaning 00110110 is the equivalent of decimal 54. That's it. That's all you have to do to convert binary to decimal. Right, 1, 2, 4, 8, 16, 32, and so on up top for however many bits are in the binary number. Write the zeros and ones underneath it, and every number that has a 1 underneath it, add that to your total, and you'll come up with a winner every time. So here I wrote the actual ones and zeros right underneath the number, and that's probably how you'd do it if you were doing it on a piece of paper. I did it because it was easier to keep the slide straight if I did it this way. But if I was doing it on a whiteboard right now, I'd write those numbers on the board, 1, 2, 4, 8, 16, 32, 64, 128. And then underneath it, I'd write 1, 0, 1, 0, 1, 0, 1, 0. And I'd say, what does that represent in decimal? And you could just look at that and say, well, oh, I got it. I take a 128. Because there's a 1 under it. I add a 32 because there's a 1 under it. I add an 8 and a 2 because there's 1s under it. And I don't add any of the other numbers. And if I add all those numbers up, I'm going to get 170. I'm done. It's that easy. Just run out the ones and zeros, add up all of the column weights in the top that have a 1 under them, and you got a winner. So let's try that second number. Here's the second number. The 00110110. I've written that out the exact same way. But on this one, you can say, well, this is easy too. I got 132 plus 116. That's it looks like 48. Plus 14. That's 52. Plus 12. That's 54. If I add those 4 numbers up, 32, 16, 4, 2, I get 54, and I've got the correct answer. That's it. That's all there is to it. It's that easy. And you'll find when we get to hexadecimal and octal, it's the same idea. We just put different column weights at the top of the screen, and we're still going to get the right answer each time. Here's the deal. Time for you to practice. I'm going to have a slide that pops up next, and it's going to have 5 8-bit binary numbers on it. And what I want you to do is pause the slide, figure out what the answer to each of those 8-bit binary numbers is, write the answer down, and while the video's paused. When you've done and got all your answers, just forward the video, and in about 5 seconds, I'll walk through the answer to each one of the problems. So what's going to happen when the next slide pops up, you'll see on the screen a countdown that goes 5, 4, 3, 2, 1, 0. If you pause at any time while it's counting down, you'll pause the video. You can try and work out the numbers for yourself. Okay, if you don't choose to do that, if you just want to go right to the answers, just let it scroll for 5 seconds, and then the answers will pop up, and I'll walk you through each answer. So you got the idea? Next slide, pause the video before the countdown gets to 0, and you can work them out for yourself, or just let the video run, your choice. Here we go. There's your 5 numbers. I'm going to count down. There's 5, 4, 3, 2, 1, and 0. So now I'll give you the answers. Okay, so here's the first number. 50101. Pretty easy. There's only 2 ones. The far right-hand one, if I were to write all the ones and zeros up top, right underneath the column weights that I showed here, I'd have a 1 under the number 1 and a 1 under the number 4. So what's the answer? Easy. 4 plus 1. Next number. Well, if I wrote that 8-bit number 1 bit at a time underneath the numbers at the top of the screen, I'd have a 1 under the 64, a 1 under the 16, a 1 under the 4, a 1 under the 1. If I added all of those guys up, I'd get 85. See the number 85 over on the right. That's how I got the decimal equivalent, or that's how I got the number that 01010101 represents. Pretty easy, I think. I hope you see that now. Well, the next number, again, let's see, we got 4 ones, and if we lay out the ones underneath the column weights up top, we're going to have a 1 underneath the 128, the 64, the 8, and the 4. And way over on the right in green, I add those 4 numbers up, and this represents the number 204. Next number. Only 3 ones here, and they would be under the number 128, 16, and 2. What's the answer? 128 plus 16 plus 2, or 146. So this 8-bit number represents the decimal number 146. And the last one, of course, worst case, what happens if everything's a 1? Well, if everything's a 1, I've got a 1 under every single number, got to add them all up. And turns out when I add up 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, I get 255. So that's what 8 ones represents in decimal when I write 8 ones in binary. That's it. That's how it works. So write your numbers up top, put the ones and zeros underneath, starting at the right, line them up, 1 number per column, 1 bit per column, keep them lined up correctly, and then if you just add up those top numbers that are on top of ones, you'll always get the correct answer. Here's the procedure. You could take a picture of this slide if you wanted to. You could write this down, pause the video and write it down, whichever is the most convenient for you. You may already remember and know exactly what this procedure is, and you're good. So whatever's best for you, but I'll walk through it one time quickly. 1, at the top of the piece of paper, write the number 1. That's what we've done. Keep doubling it to the left until you have as many numbers as the number of ones and zeros in your binary number. So if you only have a 4-bit binary number, like 1010, you only have to write 1248. Because you don't need to go any farther than the number of bits you have. Step 3, place the right-hand bit, and that's important. Got to be the right-hand bit, not the left-hand. Place the right-hand bit of the binary number under the 1 on the right, up at the top of the page. Continue placing, step 4, each 1 or 0 of the binary number under the decimal numbers going off to the left. Keep the bits in their original order. When you read the numbers back underneath these red numbers at the top, the 1s and 0s should be the same sequence that you were reading when you put them up there. And of course, when you're done, go to every number up here at the top in the top row that has a 1 underneath it. Add those numbers up. That's going to give you the sum. That sum is the number. So I hope that this has helped out. I hope that you understand this. If not, you can certainly email me. I'm Richard at TeachElectronics.com. I'm also robotics professor at Gmail. Either one, you can email, or you can go to the TeachElectronics.com site and find a place to ask a question. So glad to have you. I hope you now understand better, or really well, how to convert binary numbers into decimal. Thanks for watching.